Hello and welcome to MOOC on Applied Electromagnetics for Engineers. We have been talking about Smith chart. We derived Smith chart equations in the previous module. We will now understand those equations by plotting them. Okay. Here is for your reference the equations that we derived. The first equation that we derived was for the constant R values, and the second equation is for the constant X values. Actually they are not constants, but if you fix R to a constant value, then this would correspond to a circle, right? And similarly if you fix the value of X, this would correspond to another circle. The two equations correspond to equations of circles, one for R and one for X. Okay. Now let us first look at the constant R circles. Okay. What is the center of that constant R circles? The center is given by R by R plus 1 comma 0, right? And the radius is given by 1 by R plus 1. If you now try to plot this, you will have to consider the possible values of R first, right? We know that R will start with value of 0, which corresponds to short circuit, and R can go all the way up to infinity, which corresponds to open circuit. Okay. In that case, what will happen to the center and the radius? So for R equal to 0, the center is given by 0 0, right, because the numerator here is 0 and this one is 0 and 0, and the radius is equal to 1. This corresponds to the largest possible radius that we can consider in our Smith chart. Okay. Similarly, for R equal to infinity, the center becomes 1 comma 0, okay, and the radius becomes 0. So radius of 0 corresponds to a point. So what really happens for R equal to infinity is that the center moves away to 1 comma 0 on the complex gamma plane, and the radius of that will also shrink to 0. Any value of R should lie in between these values. For example, consider R equal to 1 circle. Okay, this will be very important. It would be very important for impedance matching. Okay, R equal to 1, in this R equal to 1 circle, the center of the circle is actually given by half and 0, right, and the value of the radius is given by half. So at R equal to, the radius of this one is given by half, whereas at R equal to 1, the center is equal to half comma 0. Okay. So let us try to plot some of these circles in order to understand what is really going on. To do that, first let us start with the complex gamma plane. This is gamma R and this is gamma I. So this corresponds to the complex gamma plane with center being 0 comma 0 and the maximum 1 comma 0 point that we would need. We will plot these 2 points first. Okay. And then look at what is the radius for R equal to 0. So when R equal to 0, the radius is equal to 1. Okay. So I can simply draw a circle with the center and the radius of 1, and that would pass through this 1 comma 0 point. Okay. I might not be drawing very nice circles, but that is because I am not a very good painting person. I cannot draw very nice circles. I will later show you how the actual Smith chart looks. You can purchase this Smith chart for about 1 rupees or 2 rupees, or you can actually find online, download and print them. Okay. So this is the circle that corresponds to R equal to 0, and really R equal to 0 corresponds to short circuit because the resistance part has gone down to 0. Okay. What about R equal to infinity? Well, R equal to infinity, the center is here at 1 comma 0, even the radius is at 1 comma 0. So this R equal to 1 corresponds to short circuit. This point would correspond to kind of an open circuit. Okay. What about R equal to 1? R equal to 1 circle must have a center at half comma 0. Where is half comma 0 located? It is located on the real gamma R axis. This is half comma 0, and with this the radius is also half. Therefore, with this as a center, half comma 0 as a center, I will now draw one more circle. Okay. This circle is the R equal to 1 circle. This circle is R equal to 0 circle, and this point that we have written corresponds to R equal to infinity circle. As R starts to increase, the center keeps moving towards this 1 comma 0 point, right. So if you were to write say R equal to 3, right, the center for R equal to 3 will be 3 by 4 comma 0, and the radius will only be 1 by 4. 3 by 4 is located at this point. Okay. 3 by 4 is located here, and it also has a radius of 1 by 4. So that circle would look something like this. So this would correspond to r equal to 3. So as the radius increases, your circles will start to shrink. When r is less than 1, okay, so in that case your circles actually would be out of this one all the time within this red radius. Okay. So this, for example, could be r equal to 0.3. You might wonder at this point, how can r be less than 1? Remember, what is r? R is nothing but the value of the actual resistance or the real part of the impedance, okay, the complex impedance on the transmission line, which has been normalized by Z0. So you can actually have the real part being less than Z0 or greater than Z0, correspondingly giving you two distinct regions. One is r less than 1 and r greater than 1. So these are the circles which are known as constant r circles. Okay. How about constant x circles? Again we will go back to the equation to note down what is the center and the radius. Okay. This time we know that the centers here must be given by 1 comma 1 by x and the radius must be given by 1 by x. So now what I have is center as 1 comma 1 by x and the radius to be 1 by x. So when x is equal to 0, where will be the center? Center will be 1 comma 0. Remember, this is the rightmost point that we have looked at. This also corresponds to r equal to infinity, by the way. And what would be the radius? Radius will be infinity. Now what is a circle with an infinite radius? It's just a line. So this will correspond to a line. On the other extreme, when x is equal to, so this was for x equal to 0. So on the other extreme, that x is equal to plus infinity, that is an inductive plus infinity, the center of the circle will be 1 comma 0. Again you will be seeing that the center will not change. The center for x equal to 0 circle is actually 1 comma infinity with a radius of infinity, and the center for x equal to infinity value is actually 1 comma 0 with a radius value of 0. Okay. So I will show you how it would look, and for x equal to 1, the center will be at 1 comma 1, okay, and the radius of this one will also be equal to 1. Okay. Finally, for x equal to minus 1, the center will be at 1 comma minus 1 and the radius will again be, of course the radius has to be magnitude, therefore the radius would be equal to 1 again, okay, except that this circle would be in the other half. So if you plot all these values of constant x circles, this horizontal line, okay, with the center at 1 comma infinity, but doesn't really matter to us, would correspond to x equal to 0 circle. Okay. Similarly, x equal to 1 circle would have the center as x equal to 1 circle would have a center at 1 comma 1 and has a radius of 1, and that would be just this quadrant. Okay. So this corresponds to x equal to plus 1 and this corresponds to x equal to minus 1. As x increases in magnitude, okay, your circle radiuses start to come down. So this is for x changing, as x increases, and when x is less than 1, they would move away into this particular quadrant. So these are the circles. They don't really look like circles, they are more like half or quadrant circles, and that is because the actual circle corresponds to this one. Okay. So the actual circle must be corresponding to this one with an appropriate center and the radius, but unfortunately or fortunately we know that all values of r and x must be mapped to within this particular unit circle, right, and because of that we really do not consider the components or the circle parts which are away from this unit circle. Okay. These will be considered when you are designing microwave and RF circuits where you will be using active devices. Okay. For them you will have to consider the circles outside of the unit circle because those devices can actually give you gain. So this superimposed constant x and constant r circles will give you Smith chart, and an actual Smith chart which I downloaded from the internet would look like this. You can see the commercial Smith chart which corresponds to superimposed constant r and constant x circles. Okay. You can see that these x circles are not really circles but they are all arcs. This was, as I said, downloaded from the internet. You can also download, and there are various circles that you can see. So I can try and maybe give you a circle that would correspond to this one. So this is, for example, a circle that would be plotted on the Smith chart commercially available, and you can see that the radius of these circles keep on reducing, eventually leading to a point. The outer periphery, which corresponds to this one, is your r equal to 0 circle, whereas this one is the important r equal to 1 circle, and this region corresponds to r greater than 1, and this region corresponds to r less than 1. So you can hopefully see all these constant r circles here. Similarly, we can also look at the x circles. Those x circles are the arcs that you can see. This hemisphere here corresponds to inductance, because for these values the corresponding values of x is positive, and below that would be corresponding values of x that would be negative. Okay. So you can see the corresponding arcs as well as the circles. There are also other markings on the Smith chart which I will explain to you shortly, but this is how the actual Smith chart would look. Now this is my suggestion for this module, and for the next few modules, please have a Smith chart with you and repeat the steps that I actually do it in the module, in the video. If you do it yourself along with me, or maybe after you have listened to the module, then you will learn how to use Smith chart. This is one of the most important graphical visual tool that is available to microwave and RF engineers, okay, and also borrowed and used by other engineers. So this is very important. Have a Smith chart with you, which will, and then navigate this Smith chart. Making navigation on the Smith chart will become easier, okay. And verification of how the problems that I would solve would also be easy in case you have a Smith chart in hand, okay. Let us come back to the use of Smith chart, the basic use of Smith chart, okay. How do we use this Smith chart in a very simple sense? As you can see, Smith chart is actually giving you a relationship between gamma and the complex impedance Z. Please note that I have dropped the normalization bar over here, okay, that is just for notational convenience, and also I have dropped this function of Z. Clearly the quantity on the left and the right hand side of this expression are functions of the position on the transmission line, but I have just kind of dropped it so that it does not clutter our equations, okay. So this value, or so this Smith chart is actually a relationship between the complex gamma and the complex Z values. Let us pick a particular value over here. So maybe we will denote that particular value and call this as the value that I have picked, and I am also circling it with I have purposefully exaggerated this circle, but this is the point that I am considering. What does that point represent? Let me also denote the center of this one of the Smith chart as point O, and the point that I have marked here as A, okay. So what does this point A really represent? If you look at it, the way this A represents in the rectangular gamma chart would be the corresponding values of gamma R, which is the real value of gamma at this particular thing, and an imaginary component or the imaginary part of gamma I. This is in the rectangular form. If you draw a line, okay, connecting O to A, then the radius of that line will give you magnitude of gamma L, and the angle will give you, or magnitude of gamma, and the angle will give you the phase of the reflection coefficient at that position. This is not gamma L. Well, you know that of course it is also gamma L, because gamma L magnitude does not change along the lossless transmission line. So this gives you, the radius gives you, OA radius gives you the magnitude of the reflection coefficient, which is also equal to magnitude of gamma L, and the angle will give you the value of the phase of the reflection coefficient. But on this chart I have circles, okay, as well as these arcs. So I have an r equal to 1 circle passing through this point. I also have an x equal to 1 circle, x equal to plus 1 circle passing through this point. So this is actually an intersection of r equal to 1 and an x equal to 1 point, okay. So therefore the corresponding impedance at point A will be given by 1 plus j1, and please note that this 1 plus j1 value that we have written clearly is the normalized value of impedance, and this is not the value of gamma R and gamma I. Please note that this is not gamma R and gamma I. This value is the corresponding impedance. To make that point little more clear, let us consider arbitrarily the point here, okay, which I have marked, and let me call this point as point B. The corresponding value of B is, I am going to specify the value of gamma r and gamma I, gamma r equal to 1 and gamma I is equal to 1. What would be the corresponding impedance here? Okay. The corresponding impedance would be obtained by going back to the equation that I have, because the normalized impedance or the impedance that I have is given by 1 plus gamma by 1 minus gamma. The impedance is given by, because gamma r equal to 1 at point B and gamma I is equal to 1 at point B, this would be 1 plus j divided by 1 minus j. So clearly 1 plus 1 would correspond to 2, this would be 2 plus j divided by 1 minus 1 is gone, so therefore this would be minus j down here, and what you get is minus 1 plus 2j. This would be the complex impedance that would be represented by this plus, point B. But what exactly is this? How can we think of the impedance as minus 1 plus 2j? Clearly it is not. The reason why it is not is because we considered the completely unphysical scenario of gamma r equal to 1 and gamma I equal to 1. What would be the magnitude for point B? The magnitude of point B will be equal to square root of 2, and square root of 2 is greater than 1, making the magnitude of reflection become greater than 1, which cannot happen in a passive circuit. Let me tell you once more. Point A that we considered lied within the unit circle of the Smith chart. There the value of magnitude of gamma L was less than 1. There was a certain phase with it, but let us not worry about the phase. The corresponding value of gamma r and gamma I can also be read from the chart. But most importantly, the point A represented the intersection of the constant r and the constant x arcs, right? The constant r circle and the constant x circle, and in that case correspondingly we obtained the value of impedance as well. You can check that out. So with the value of A given as say 0.5 plus j 0.5 in the for the gamma value, you can find out what would be the corresponding value of impedances. Okay. So every point inside the unit circle corresponds to a physical value of impedance, and the same point will also tell you the reflection coefficient. Okay. It only depends on what coordinates you are considering. If you consider the circles and the arcs, then you are in the impedance coordinates. If you consider the straight rectangular axis, gamma r and gamma I, then you are in the complex gamma plane, and hence those points correspond to complex reflection coefficient. And clearly for points which lie above or outside of the unit circle, such as the point B that we considered a few minutes ago, the corresponding value of gamma, magnitude of gamma will be greater than 1, and that cannot happen for a passive load that we have considered. A passive load cannot reflect voltage which is higher in magnitude than what it has received. So the reflection coefficient will always be less than 1 for a passive load. It's another question that if you actually have an amplifier, then the reflections from an amplifier being an active device, can reflect back a voltage or current which is greater in magnitude than what is receiving. Okay. In that case, yes, those correspond to a proper point, but in that case R would be negative, but we have already said that R negative corresponds to a gain rather than loss. Okay. Negative resistance corresponds to gain and the presence of an active device. But mathematics doesn't care. You can specify any value on this rectangular chart. You can specify here, you can specify this point, you can specify maybe this point. For each of these points, the equation will faithfully give you what is 1 plus gamma by 1 minus gamma, but the result of z that you get will be completely nonsense, except the results that you get when you lie within this region. Okay. So this colorful slide is the summary of our Smith chart, and the basic ways of using the Smith chart is what I will tell you next. Okay. So we already have seen the Smith chart, right? Let me just draw a basic Smith chart for you. As I said, please have the Smith charts along with you when you are listening to these videos. That will help you reinforce the concepts that we are talking about. And you can also notice couple of peculiarities with the Smith chart. The Smith chart, all points, okay, will pass through this 1,0 point here. Okay. Also this point, so suppose now consider the complex impedance Z to be open circuit. For the open circuit, and assuming that it is only the real part R that is becoming open circuit, this corresponds to the circle and this corresponds to the radius. The phase angle for an open circuit is also equal to 0. Therefore, this is really the open circuit point on the Smith chart. Similarly, when you consider r equal to 0, that corresponds to this circle, but then r equal to 0, if I also look at the phase for a real impedances, right. So, if I consider real impedances and for which x equal to 0, x equal to 0 is this line and r equal to 0 is this line, therefore, the intersection of those 2 points must correspond to short circuit. Okay. So, this is between the short and the open circuit along this line is the value of r which goes from 0 to infinity, where x is simultaneously equal to 0. So, this is all real impedance line. Okay. This is all real impedance line. So, this point here is the open circuit point, this point is the short circuit point. If you want to enter the Smith chart, or if you want to locate any impedance on the Smith chart, all you have to do is first take the impedance, then normalize the impedance by dividing by Z0. So, you are going to obtain the normalized impedance. This normalized impedance will be the intersection of R and X, circle and arcs, right. So, for example, let us say Z bar, the normalized impedance is 1 plus J3, okay. The normalized impedance is 1 plus J3, then all you have to do is to locate the R equal to 1 circle, which happens to be this one, and let us say the X equal to 3 circle, which is located at this point, okay. So, the intersection of these two would correspond to the point. So, this is the point A, which corresponds to the normalized impedance 1 plus J3. Again, the meaning of 1 plus J3 is very clear. At this point, the impedance, if you unnormalize, you simply have to multiply by Z0 to unnormalize. The impedance is actually given by Z0 plus J3 into Z0. If Z0 is equal to 50 ohms of that particular transmission line, the impedance at this point A was actually given by 50 plus J150 ohm at a given frequency. Okay. The other important point about Smith chart is that impedances are periodic. What do we mean by the fact or the statement that impedances are periodic? Consider the simple scenario of a short circuit first. Okay. Suppose I consider a transmission line and then short these 2 terminals. Okay. So, I create a short circuit. We know very well in one of the previous modules that as you move along the transmission line, the impedance changes, and if you move a distance of lambda by 4, the short circuit would actually look more like an open circuit. In fact, it would look like an open circuit. This is the quarter wave transformer that we have talked about. And once more, if you move a distance of lambda by 4, then the open circuit would be transformed into a short circuit. So, the impedance at this plane is exactly equal to the impedance at Z equal to 0 plane. So, whenever you start with any impedance, it does not have to be at the load, it can be at any point Z that you start, and then you move a total distance of lambda by 2, that would correspond to going back to the same value of the impedance. This is for lossless cases. So, impedances will repeat every lambda by 2. So, when every lambda by 2 impedance is repeating, what it means is that the angle 2 beta Z must be going to 2 pi rotations, right. So, you start with 2 beta Z, we know that beta is 2 pi by lambda, and when you take Z equal to lambda by 2, you see that this total phase would be 2 pi, which corresponds to 1 complete rotation on the Smith chart. So, I can start at point A and go along the constant radius OA, which corresponds to a constant corresponds to the constant gamma circle, and when I travel completely at 1 rotation, which corresponds to lambda by 2 movement away from the load towards the generator, I land back on A. So, that is the meaning of impedances being periodic, and therefore, when you move lambda by 2, you come back to the same point that corresponds to a 360 degree movement or 2 pi movement on the Smith chart on the constant gamma circle. But if you move only lambda by 4, then what you actually end up is on the opposite side of this, okay. Diametrically opposite side, it is not really nice as I said the circles, but if you do it on the actual chart, then you will be able to get this correctly. So, when you move only lambda by 4, then you will land up on the other side, and here the impedance would be inverted, because what is the lambda by 4 transformer length doing? It changes the impedance to Z0 square by Z. So, you start with the loads, then this would become Z0 square by ZL, and this would be the new impedance that you would see at lambda by 4 distance. But I know that this Z0 square can be distributed equally to Z impedance and ZL. That is, I take this Z0, divide both sides by Z0, and what I get here would be the impedance at lambda by 4 distance, which can be normalized, will be equal to the normalized value of 1 by ZL bar, and 1 by ZL bar is the normalized admittance YL bar. This is, we started with the load, you can start with any value of the impedance that you want, okay. So, it does not really have to be that, but the important point is that you start at one point on the Smith chart and you move lambda by 4 distance, you end up with diametrically the opposite point on the circle. This point would correspond to the normalized admittance corresponding to the normalized load here. So, this would be the normalized load ZL bar, and this corresponds to the corresponding normalized admittance. In fact, this allows you to use the Smith chart as an admittance chart also. Why? Because I can go back to this Smith chart. If I want to add admittances or do something about the admittances, and I only know the impedance to begin with, I start with the impedance, draw the constant gamma circle, and then move a distance of lambda by 4, landing onto the opposite point, giving you the admittance that you would have seen at this particular point. From now onwards, you can think of the chart as admittances, but in market you will also get an admittance chart which looks like the inverted, you just take this Smith chart and then invert it. So, wherever you had the constant r equal to one circle, that circle would now be along this way, and then you start getting these circles. So, the circles would just be inverted. So, every behavior is just inverted, okay. You will also get additionally few more larger circles. So, this is how you actually get an admittance chart. Sometimes in market you will also get what is called as a ZY chart. In the ZY chart, which will be slightly confusing to you, which is what is I think would have both impedance values as well as admittance values superimposed, okay. But these ZY charts are quite useful for impedance transformation problems. You can buy or you can download a ZY chart and work with it. For most cases, you are satisfied with just working with the Smith chart, starting with the impedance and then converting the impedance into admittance. So, this brings an end to our Smith chart basics. We have derived the Smith chart equation and we have looked at how to basically use the Smith chart basic calculations. From the next module onwards, we will look at a few applications which require us to use the Smith chart and learn how to solve the transmission line problems. Thank you very much.